Let me give you an economic illustration, a simple economic illustration of an optimization problem. It's the same methodology used to solve it, only the notation is a little different for an economic problem. Instead of using y and x, let's use P and Q, and revenue and costs. Okay. Let's just take a very simple economic problem. You have a monopoly. A monopoly is a single seller of a good. And this monopolist can charge whatever price they like for the product. Then consumers will decide how much to buy. The demand curve, or actually the inverse demand curve, is this. P equals 50 minus 1/2 Q. This is the inverse demand curve. At any given price, this inverse demand curve shows you how much consumers will buy. Okay, if we graph this demand curve, it looks like this. Let's measure P on the vertical axis and Q on the horizontal axis. Just a straight line with a slope of minus 1/2. Vertical intercept's 50. The slope, minus 1/2. So it crossed down here at 100. Okay. The monopolist can charge any price he or she likes. Then consumers will decide how much to buy. If this monopolist wants to maximize its revenue, what price should the monopolist charge? Suppose this monopolist doesn't have any variable costs of production. All the costs are fixed costs. And so the goal of the monopolist is just to maximize revenue. What price would maximize revenue? Or alternatively, what quantity would maximize revenue for the monopolist? You want to maximize revenue, so that is our goal. Let R stand for revenue. Well, what is revenue? That's where you should start. What is revenue? Since that's what we want to maximize. David, what is revenue?
Revenue is how much money they're making.
Right. Okay. And in symbols, what would that be? R, but what else? R equals, price times quantity, P times Q.
Okay.
See, that'll help us. If we just leave it at R, that's not going to help us. But by definition, revenue of a firm is the price per unit you charge for your product times the number of units sold, P times Q. Now, revenue right now is expressed in terms of two variables, P and Q. What can we do to simplify this problem? To make it more manageable? Yes? Yeah, substitute in for P. Actually, you could do it either way, but I like your suggestion best. And you substitute in for P. Notice P is equal to this. So if we substitute in for P, then we can express revenue as 50 minus 1/2 Q times Q. Now we've got revenue expressed as a function of a single variable. Okay, and we can simplify this equation to be just 50Q minus 1/2 Q squared. Now we've got revenue expressed as a function of Q alone. R of Q is given by this equation. In many word problems, this is the most difficult thing. is to figure out what is your objective function. What is the thing you're either trying to maximize or minimize? Once you've got that, the rest is mechanics. Okay, so David, our goal is to maximize revenue. How are we going to do that? We got our objective function there, revenue. We want to maximize our revenue. So how are we going to go about doing that? Okay, and then, okay, David, then what do we do with that derivative? That's a good idea. Let's take the derivative. In fact, that is our first order condition. All right, so r prime of q is just 50 minus q, isn't it? If I differentiate that. Okay. Now, what do we do with this? Exactly. Because what we're trying to do, David, is to find what? Exactly. And we call this value of q, where the first derivative equals 0, we call that value of q the critical value of q. Okay. In this case, our critical value of q, we'll call it q sub 0, is equal to 50. At q equals 50, David, that is where the first derivative is 0. That's where the point slope of the function is 0. Okay. Now, can I be sure that we've actually maximized revenue? What do I need to do to make sure that revenue is a maximum?
Second derivative.
Exactly. Take the second derivative. And what is the second derivative, David? Yeah, it's negative 1. And it's negative 1 for all values of q. So what does that mean then, David? Okay, the second derivative is negative. Right. That guarantee the second derivative is negative everywhere. So it's certainly negative here. So we know that r double prime of q at 50 is also minus 1. So at q equals 50, first derivative is 0, second derivative is negative. That guarantees we have a relative maximum at q equals 50. Okay. And again, let's graph it. Oh, let's note one more thing before I leave this domain curve. If q equals 50, what does that mean about the price being charged for this product? If you're producing 50 units, what price is the monopolist going to charge? 25. The monopolist is going to charge as much as he or she can at that and sell that output. So they would produce 50 units, sell them for $25 a piece. And then the maximum revenue would be $25 times 50 units would be 1,250. Okay. And let's graph our revenue function. Here's our revenue function. Let's look at the graph of this, see what it looks like. We know this is a quadratic, so its graph is going to be a parabola, either U-shaped or upside down U. In this case, the coefficient on q squared is negative, so what is it going to be? Its shape is going to be, Andrew? It's going to be upside down U, yeah. And the graph will just look like this. Obviously, at q equals 0, a revenue is going to be 0. And at q equals 50, 50 is our critical value. We know that the first derivative is 0 there. And we know if we plug in, this is 1,250. And right here, this point, the first derivative is 0. and the second derivative is negative. So a negative second derivative means as q, if you go to left to right about this point, slope is going from positive, 0, negative. That's a negative rate of change. It's going positive, 0, negative. As q gets bigger, that's a negative rate of change. So it has that kind of curvature that guarantees that we have a relative maximum right there. Okay, so a simple optimization problem.